Always watching.
Any suggestions on videoing anywhere? Please let me know.
Dr. Stevens,
Yes, question.
is it a good idea to watch last semester's Organic 1 videos?
Can't hurt.
Okay. Should be relatively the same.
Yeah. Okay, how are we doing on the DQ? Singular. If I get a formula for I wrote it in blue. I don't know why it's not showing up as well. It seems maybe I'm just not seeing as well. If I get a formula for singular, how many carbons? Got to get used to these line bond structures. 35? How many hydrogens? Okay. 35 carbons, 36 hydrogens, yeah? How many nitrogens? Duh. How many oxygens? Sulfur, 1. Chlorine, 1, yeah? Put them together, you got singular. Triasma, is that right? Functional groups. You see any functional groups? DUS? How do we do on this? Any questions about this one? Question?
Does the triangle count as a ring?
Sure. Yep, triangle. It's a cyclopropane. It's a ring. Yes. Yes. That's a small ring. You can also have huge rings. Huge rings. Relating to the question you asked earlier.
Yeah,
Have you already found it?
I figured it out.
Oh, okay, that's quick. Okay, let's get going. Functional groups, let's finish those up. Functional groups with carbonyl groups. Checking in the lab tomorrow and Friday, yeah. We'll meet upstairs at 2:30. Yeah. We'll get started at 2:30. Directions for checking in the lab manual. Requirements for the day, etc. Any questions about lab at this point? Shouldn't be. Everything's there. Come to lab and check in. Okay, functional groups. We looked at carboxylic acids. Carbonyl, carbon on one side, it could be 1 carbon or it could be 300 carbons. OH on the other. This is going to be acidic proton. Okay? The only functional group that's called a so-and-so acid. Carboxylic acid. By the way, this is an abbreviation of the functional group, COOH. Sometimes you may see CO2H, 2 O's, 2 O's, maybe sometimes just set it with a 2. Okay? That's this portion on the end, CO2H. The 2 O's are not bonded together. This is sort of condensed. We'll mention those a little bit later, a little bit. Next, ester, carbonyl. Carbon group on one side, O carbon on the other. If it's OH on the other, it's a carboxylic acid. But if it's OR, like an O methyl or an O huge whatever carbon, ester. Ester. Next, amide. Amide, I usually say amide. Some people say amide. The long name is actually carboxamide. Carboxamide. It's a long name, but usually it's just shortened to amide or amide. This is carbonyl, carbon group on one side, nitrogen on the other. Now with all your nitrogen functional groups, when you start putting R groups on, the name doesn't change. Here you start using primary, secondary, tertiary. You put an R group on the oxygen here, it becomes a different functional group. You put an R group on the amide, it just becomes primary, secondary, tertiary. We saw this previously, but again, primary, this refers to how many carbons the nitrogen's bonded to. If these are two H's, the nitrogen's bonded to just one carbon, so it's primary. Secondary would be where one of these is an R group. Tertiary would be where both are R groups. If both are R groups, it's 1, 2, 3. So they're all amides. Acid chloride, also known as an acyl chloride. Carbonyl on one side, R group on one side, chlorine on the other. Now you can also have acyl bromides and acyl fluorides. The chlorine is most common here. That's why it's the only one shown. Acid chloride. Those tend to be pretty reactive. Those are mainly covered in organic 2. There's two additional ones that I want you to know. The nitrile. This has the cyano group. C triple bond N. C triple bond C is your alkyne, right? C triple bond N is a nitrile group or cyano group. So the carbon's going to have an R group, nitrile, cyano. What's the answer? Nitrile or cyano? Either really works. Nitrile is the compound as a whole, cyano is the specific group. Either works in either case. That's analogous to, on the previous page, most analogous to like alcohols. This is called an alcohol because it contains the hydroxy group. A nitrile is called that because it contains the cyano group. They're interchangeable. You can call that an alcohol group, but it's probably best to call it a hydroxy group. With cyano and nitrile, they're completely interchangeable to me. I also want you to know the sulfonamide. It's actually another type of amide, but it's never shortened. Only the carboxylamide is shortened. Sulfonamide. Some people may say sulfonamide. Sulfonamide, pretty good. If this was a carbonyl, right, don't draw it, that would be a regular amide. Carbonyl, R group, nitrogen. This is where the CO is replaced by SO2, which is sort of like a sulfone. So it's sort of like a sulfone amide, sulfonamide. Now, this can be primary, secondary, tertiary. We can start putting R groups on the nitrogen and it's still a sulfonamide. I want you to particularly know this. This may not be in hardly anybody's textbook. Even Wade may not have this one. But I want you to know it because it's in a lot of drugs. A lot of anti-diabetic drugs, a lot of antibacterial drugs. And so sulfonamide to me is just an important one to add. Nitrile is just about in any list. I don't know why Smith left nitrile out. Although it's in later chapters in Smith. Okay, down here is just some example assignments. Atenolol, yeah, used to treat heart conditions. You got this amide here, right? Primary amide, right? Primary amide. Primary amide. Gotta be careful. Sometimes students want to say this is an amine and a ketone, just real close together. No. The carbonyl is bonded to a nitrogen. It's an amide. It's not a ketone. It's not an amine. Aromatic ring, granddaddy of them all, benzene ring, ether. Oxygen with two R groups, two carbons. Alcohol with the hydroxy group. That's an amine because it's nitrogen is only bonded to plain carbons. If it's bonded to a carbonyl, it's no longer an amine with an N. This amine, what substitution is this amine? Secondary amine because it's bonded to two carbons. Okay, examples over here. Sulfur bonded to two carbons, sulfide. By the way, it's also called a thioether because, see, if that was a sulfur, same bonding as oxygen, we call it a sulfide. Thioether is also kind of a slang name. Thio meaning sulfur. It's like the sulfur equivalent of an ether. Okay? Other functional groups here. A couple of other ones here I want you to know. Some special alcohols. Right here. If the OH group is on an aromatic ring, it's an alcohol, OH and then a carbon. It's a special name. It's called a, where's it at? Is it not showing up?
Second line in the bracket.
Oh, it's written. Called a phenol. It's got the OL ending like an alcohol. Okay, OL, not YL. YL means something different. Phenol versus phenol. Some people say phenol. I say phenol. Special type of alcohol. And usually you always want to call it a phenol. If the nitrogen is bonded to an aromatic ring, it's a special type of amine called an aniline. And then even if you start putting things on the nitrogen, it's still an aniline, just now substituted. So please also know those. Very common as you move forward. They have unique reactivity, so we're going to give them the more unique name. Okay, I left my workbook upstairs, but in the workbook on one of the first pages, page 3, is a whole list of drugs. And it asks you to identify functional groups, it asks you to identify DUS, it asks you to do a lot of things. So there's certainly a starting point in the workbook. Okay? And then on the next page, it's like some Lewis structures, etc. I know some of you are already doing that because you're already asking questions. You can also, there's also structures in the syllabus page. So you start doing these for practice. It's also good to make flashcards with functional groups. Flashcards can work for a lot of things. Some information on the front, maybe structure on the back. Just writing them out helps you learn them. And then you got them to test yourself. Ooh, I can't remember that one. Oh yeah, amide, forgot. Question?
So for the nitrogen bonded to the benzene ring, it's still, that nitrogen can still be primary, secondary?
Yes. Yeah. The one drawn is primary. You can have tertiary animals. If you start putting R groups on the nitrogen, I think most any nitrogen functional group it goes by primary, secondary, tertiary, but not the oxygen functional groups. Those get different names. Got one handout here. Acid-base chemistry. I sent you one by email over the weekend. One handout, it's yellow. One I sent you to print was physical properties. We'll be getting to that one next. This comes after physical properties. But that doesn't mean you can't be looking ahead. Acid-base chemistry, very important. You guys tend to need some work on acid-base chemistry. Okay. Where's our outline at? Functional groups, yeah. Okay, your functional groups, I'm on the outline, green. Your functional groups, you know them, etc., but they're also building blocks. Because any structure you're going to draw, unless you start, there are a variety of other functional groups that you'll never see in organic. They're kind of more advanced. You'll see a couple more in organic too. But usually any structure you're going to see or draw at this point, or most all drugs, are going to contain those functional groups, those particular arrangements. When you're asked to put together structures, you can use functional groups as sort of prearranged building parts. Down here near the end, under Roman numeral 3, I said, give a structure for C7H6O2. First off, how many degrees of unsaturation in that formula? 7. 2n plus 2 is 16. Only got 6, missing 10. 5 by 2, 5 DUS, right? So any structure you draw better have 5 DUS. Okay, it's got 7 carbons. I can get 6 carbons on the board just by drawing a benzene ring. It's a prefabricated structure. Who said I can't? I guess I'm dealing with 7 carbons. I'm dealing with 5 DUS, right? How many DUS are on the board already? 4. 6 carbons, okay? 2 oxygens. You know any functional groups with 2 oxygens? Or even just 1? Well, how about this? What about a carboxylic acid? Stick that on there. Now I got 5 DUS on the board. C7. How many carbons I got on the board? 6, 7. How many H's I got on the board? Actually 6. How many oxygens I got on the board? 2. There you go, there's the structure. You see, I didn't put it together one atom at a time. I used pre-built, fabricated, like building a house, you bring in everything and put it together on site. That's using your functional groups and your DAS information. That formula is the formula written right there. You see how I did that? There are a variety of other structures I could have drawn for that formula, because there are a variety of other constitutional isomers, right? Okay, hybridization. Hybridization is needed for a good number of things. You need it for IR because you talk about sp3CH bonds, sp2CH bonds, that's hybridization. You also need it for talking about bond angles, etc. You guys should have a good foundation of hybridization. Let's look at methane, Ch4. If we drew it quickly on the board, we'd probably just draw something like this, right? 4 bonds, we did that before. Yeah? The problem is this is not a good structure. Because from 9th grade geometry, this looks like 90-degree bond angles, right? It also looks like it's flat on the board. We know from experimental evidence that the bond angles are really 1 and 9.5 approximately. We also know that it's 4 equivalent bonds. You can almost just see that from just this simple structure here. I mean, why would one CH bond be different than the other? And again, we know this from experimental evidence. Just about everything we talk about is based on stuff that came out of the lab and it's been turned into theory. Keep that in mind. So, let's start talking more about these bonds a little bit more than just overly simplistic. How are we going to make 4 equivalent bonds if the ground state configuration of carbon looks like this? These are the orbitals we use to make bonds. These are the valence orbitals. Ground state looks like a lone pair. 2 electrons, that looks like a lone pair. We have to bring in 4 H's, and each H brings in an electron. Why do we bring in 4 H's? Because we can bring in 1 electron. I'll draw the electron as an H to clarify that it came from the hydrogen. And we can make a carbon-hydrogen covalent bond, 2 electrons that are being shared in an orbital. And we can make another one. But then what are we going to do here? We've got to bring in 2 more H's. That's 2 electrons from hydrogen, but it looks like are they bonded to each other, or is it a lone pair? To me, this looks like 2 lone pairs and 2 bonds to H's, after we just say it's all electrons. But we don't have 2 lone pairs. We actually got 4 equivalent bonds. Ground state is not going to work. I don't know what ground state works for, other than to give you something to do in Gym Chem. When these guys bond, they bond in a mixed state. These reorganize. We call that, we get a fancy word. Fancy word for mix is hybridize. Okay? This is going to hybridize, or mix. Let's call it mix, because that's only 3 letters. And what we really need is a setup where we take these 4 orbitals, and instead, let's just have, now putting the energy right here in between, boom, 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 boom. What if instead if we had 4 like this, we had 4 like that? Now we can say the valence electrons of carbons, if we fill these in, by the way, these are all degenerate. Everybody knows what degenerate means, right? Somebody was asking. Same energy? Just a fancy word, right? And if we fill these, Hund's rule, off-ball principle, one goes here, where's the next one go? So you know all that, right? How to fill your orbitals? This would be sort of the starting state, valence. Now we can bring in an electron from H and make a covalent bond. Electron from H, electron from H, electron from H, and we can make 4 equivalent bonds. Because they're all using 4 equal orbitals. That's how we need to bond to match what we know from lab. But instead of the ground state, this is a hybridized state. Or hybrid state. Or configuration. And yes, this is energy. What do we call these orbitals and what do they look like? Are they s orbitals? No. Are they p orbitals? No. They come from combining these. Now, does the atom sit there and combine them, like making cookies? No, the atom just does this naturally. This is nature. The combining is really referring to math. A lot of this is based on math. But you can do math where you sort of combine all this and get a different answer. And combine them this way. And you can theoretically do all the math to match that type of layout. Ultimately, we're combining the S and the 3 Ps. We call those sp3s. Each one is it's 4 sp3 orbitals. That's an sp3 orbital, that's an sp3 orbital. The name just comes from what was combined to make the orbital. It's pretty simple, right? 4 sp3 orbitals, they're equivalent. What do they look like? We know this is spherical, that's dumbbell. What if you start combining them, what's it going to look like? Well, when I combine all 4 here, it can be kind of difficult. But let me show you if we combine just 2. By the way, I was thinking yesterday and this morning, wow, I hope they have did some reading. I hope they got some background information. I could sit here and talk for an hour and give you the background. Why it's all important. Guess what? We don't have time for that. And the expectation is you're going to read and get that sort of primer from your textbook. And see, and it talks for a couple of pages. I can't sit here and read to you and just talk to you for 30 minutes. You've got to get into it. But if you're not reading, you're not ready to come here and understand it. Okay. Let's see. Let's just combine a P with an S. Okay? Here's a P, here's an S. They're on top of each other here in this, and I'm going to kind of combine them. Now, the S has some phase. Let's just call it positive. The P has phase too, but this is different from this. Now, over here, the positive phase interacts with the positive phase of this, and it reinforces it. It gets bigger. Okay? And the nucleus is right here. So over here, we're going to have, this is like 2 waves in the ocean coming together and making a bigger wave. So over here, we're going to have sort of a bigger orbital. And you know all that background of what an orbital is, right? Over here, the positive of the S cancels out negative of the P, different phase. And this is like 2 waves coming together, but they come together and cancel each other out, which can happen. Both in the ocean, also sound waves. You can get places where there's no sound because the waves cancel out. So over here, it actually may look like this. And this is sort of trying to show what an sp orbital will look like. We call it sp because we combine an s and a p. All right? We'll do more of this. I got a little drawings in the handout. This is the back lobe. sp hybrid, okay? Anytime, just to reinforce, anytime we mix, it's hybrid orbitals. Back lobe is usually not drawn. So when we start putting these around the carbon, I won't draw them. All right? But it's there. And actually, we'll refer to it at the very end when we talk about backside attack. So now we got 4 orbitals. Let's put these around the carbon now. By the way, if we put these p orbitals around the carbon, how would they be oriented? What would be their bond angles to each other, angles to each other? You learn in Gen Chem that p orbitals are all orthogonal, 90 degrees to each other. Okay? That's another reason this is bad. If these are 90 degrees to each other, how do we get bond angles of 109.5? You can't. That's why this is no good. But here we got 4 things equivalent, and 4 things are best spread out how? Tetrahedral. Now I'm going to draw in his bonds here, or his just lines, because that's easier for me. And then I'm going to draw something like this. And by the way, I'm not going to try to make an S with 3 P's. I'm not sophisticated enough. It's going to get too 3D, and okay. I started with just combining one of each, more simple. We'll talk about the difference between the different hybrids as we move along. 4 of these are oriented around the carbon in a tetrahedral manner, like this. Okay, this is really supposed to be an orbital. All right. Now, when I draw this, it may look like a P, but this, okay, but it's a hybrid. I'm not always going to clarify this difference here. Now, there's the back lobe, right? Don't draw anything. Because we're not going to draw the back lobes, because it's going to make it too complicated. Right? So we're never going to draw them again. All right? There's one of them. Here's another. And I didn't draw the back lobe. All right? That's in the board. The other 2, we're going to have projected this way, but it's going to be a little bit forward. Okay? And we do that with a bolded. It gets bigger as it comes more closer towards you. And the other one is going this way, but it's going kind of away from you. So it starts out big, but it tails off. Now hold on, I might actually draw this a little bit. Again, we don't need to be so particular. My drawings will never be as good as we're going to see in the book. We got to know that, okay? But this is an orbital coming this way, right? 4 back lobes, we didn't draw them. Let's make it a little cleaner. Let's just do boom, boom. I reckon we can get rid of this. Boom. Same thing. Because going forward, we're going to just know that that's an orbital. So here are your hybrids around the carbon in a tetrahedral manner. Why tetrahedral? Because it gives more room. It gives more room. And in a tetrahedral, all the bond angles, as illustrated by this one, are what? 190.5. That can vary a little bit. But it's certainly not 90 like we had for carbon. You already got it drawn. It's certainly not 90 like that. Now what's this orbital doing in methane? It's interacting with the H orbital to make a fancy covalent bond. What type of orbital is the H using? By the way, these are sp3. All these are sp3 orbitals, right? 4 sp3s arranged in a tetrahedral nature. What is this orbital doing in methane? It's interacting with the H orbital. What orbital is the H using? The 1s orbital. That's all it's got. 1 electron, 1s, right? What's the shape of that?
Spherical.
Spherical. It's not hybridized, anything. It's spherical. Okay? It's the H. It's spherical. Right here's your magic. 1 electron from carbon, 1 electron from H. We can put it like this. There's your covalent bond. Made by what type of orbitals? Overlap of a sp3 hybrid from carbon with a s orbital from hydrogen. 2 electron covalent bond. Book that thick. Right there. We just do that 4 times, right? I'm not going to fancy it. Just 4 times. Let's just focus here. So this is sp3 s. This is a sigma bond. Sigma. What's a sigma bond? You discussed sigma bonds in Gen Chem? Orbital overlap, all this good stuff. Hopefully all this is mainly review, right? Sigma bond. What's a sigma bond? Sigma bond. Bam, I just made a sigma bond. Sigma bond is head-to-head overlap. Okay? I can't turn around because these don't, but consider that the other head. Boom, head-to-head overlap. Sigma bond. Okay? The head of each orbital is here. Not side to side. If we bonded these together like this, some glue or whatever, some type of attraction, that's side to side overlap. That's going to be a pi bond. Head to head, sigma bond. One thing about sigma bonds is they can rotate and still be bonded. Pi bonds cannot. If we try to rotate this, we're breaking the bond because it's no longer full side-to-side overlap. Sigma bond, rotate. You got 4 equivalent sigma bonds here. Spread out in a tetrahedral nature. 4 regions, because 4 regions gives the most space. With 4 regions, we now have 109.5 bond angles as opposed to 90. And I said before, if you bring in 4 balloons and tie them all together, guess how they will spread out? They'll spread out in this manner. All right, let's move forward. There'll be more questions that we can fill in here, but we got to move to a different example. Ground states there. Questions while I'm erasing? Things build. Things build. B, ethene, C2H4. Ethene is going to look like the ene ending means it's an alkene. We've got to have 2 carbons to have an alkene. Slang is ethylene. Okay, there's some information there. It has 1 pi bond. We'll see that here. Okay, we need to just get into it here. The starting point for me is how many regions around the carbon? 3. Single bond, double bond. Double bond is 1 region. 3 regions. That's different from methane because methane has 4. 3 regions are best spread out how? 3 balloons tied together will spread out how? Trigonal planar. And trigonal planar is synonymous with sp2. sp2. And both carbons are the exact same thing. They're both sp2 hybridized. sp2 should mean to you that we combine what? An s and how many p's? We only combine 2 p's. Now I'm not going to draw it again, what it's going to look like. We'll get to it. So we're going to combine this, but only 2 of these. Real lightly, I'm going to say I'm going to combine these. Not going to do anything with that. Forget the H's, because that's just ground state. We're going to mix. And we're going to have 3 hybrids. By the way, which is going to be higher in energy, sp3 or sp2? What's the energy difference? For example, when I put the sp3s, I put them up sort of right in between, right? If these were there, where would I put sp2, higher or lower? The answer is simple. Look at what went into here. This is 25% S. Because it's 1 out of 4 is S. What percent S is here? 33% S. Because it's 1 out of a total of 3. 1 S, 2 P. More S character. Since it's more S character, it actually looks more like an S. So if I tried to draw them all, if it looks more like an S, it's going to be more rounded and fatter. Same thing with energy. More S means it's going to have energy more like an S. And S is lower in energy. So the more S character it has, the lower the energy. It's just like blending colors or ice cream. The more chocolate you put into your mix, if you're mixing chocolate and vanilla, the more chocolatey your mix is going to be. More S character. So the sp2s are going to be lower in energy. But I'm not really putting all of them up here, so it's not really relevant. We can't compare. Three sp2 orbitals. We're going to say we got this set up. But what else is here that we didn't mix? P. You guys tend to forget about that P that we didn't mix. It's still there. And the electrons sit like this. This is 3 regions. Your hybrid orbitals set the regions. 3 regions, we thus need 3 hybrids. 4 regions, we thus needed 4 hybrids. Here's the carbon. Boom, boom, boom. Here are your 3 regions. Trigonoplanar. Planar meaning it's all on the plane of the board. Nothing's coming forward, nothing's going back. I didn't show it exactly when it was up there, but the tetrahedral we had. We make your tetrahedral. We had 2 in the plane. Act like the board's here. 1 forward and 1 back. That was your tetrahedral we drew. This is trigonoplanar. Bond angles are trigonoplanar or what? 120. Yeah, all those are 120. Okay? But these are orbitals. And this is an sp2. And it's an sp2. sp2. Now again, don't worry about the shape. We'll compare them all at the same time later. Not drawing the backloads. This one's interacting with an H. We've already done that. I'm not going to put electrons in and talk anymore. That's interacting with an H. What is that one? What is this orbital interacting with in this molecule?
Carbon.
Another carbon that's the same exact setup. Same exact setup, trigonoplanar. Okay? Trigonoplanar. Trigonoplanar. We want to draw lines to help us. And so that's sp2, sp2, sp2. I'm not going to finish that up over there, but right here is important because right here we have a carbon-carbon. What type of bond is this making? No, that's just one bond. It's two orbitals interacting to make one bond. There's no double bond there yet. What type of bond have we made? Sigma bond. Sigma bond using hybrids. Hybrids make sigma bonds always, I think always. What's left over on this carbon? Because the three hybrids are there, and we made bond to H, and bond to what? Carbon. Again, these are electrons. One electron from H made bond to the other electron. One electron from H, one electron from carbon. These are three sigma bonds. P orbital's there though. On the carbon, how is it? I'm going to make it a little skinnier compared to the hybrid orbitals, because the hybrids have S character, they're fatter. It's there, and it's orthogonal to that. It's perpendicular to it. If that's all on the plane of the board, this is actually sticking out and going back. But it's there. The other carbon's the same thing. And this has one electron in it. Okay? That's one electron from carbon, one electron from the other carbon. One electron in it. But guess what? This other guy has one electron. And guess what? These two p orbitals are actually interacting. But they're interacting how? Side to side. Now what type of bond is that?
Pi bond.
That's a pi bond. Pi bond using what type of orbitals? P orbitals. But the pi bond is perpendicular again. I wish I had better models for these other hybrids. The original was here. Just look at that carbon. Bond, bond, and going that way. The p orbital is coming straight out. Okay, here it is on the board. Coming straight out at you. Okay? Let me turn it up like that. If I want to draw the bonds, the p orbital straight up, we got to turn the hybrid system flat this way. But they're coming straight up, and they're interacting side to side. Now you might think, how can this orbital interact with this orbital? Well, that's because of my drawing. I kind of have them a little far apart. They're kind of skinny. In chemical life, they're a little closer, and they're a little fatter, and they have some side-to-side overlap. But guess what? The overlap is not great. A pi bond is weaker. Pi bond tends to be weaker. Sigma bond is good head-to-head. Okay? So how many bonds do we have between the carbons? Two. A sigma and a pi, and we call the two a double bond. How about that terminology? Two is double. Sigma bond, pi bond. That's why whenever we look at a double bond, we see how many pi bonds. A DUS, a pi bond is a DUS. I see one pi bond here, right? And a sigma, that's why it's called a double bond. Important with a pi bond is, can these two carbons rotate? Can I hold that one and spin this one? No, because if I try to spin that one over here, the pi bond will have to break. The pi bond with full side-to-side overlap keeps it from spinning. We'll talk more about that going forward. Let's look at SP. Let's try to get to that. We'll summarize. We're doing some reading. SP, probably ethine. Is that the next compound? Yeah. Yeah, both carbons are sp hybridized. How many regions around this carbon? Two. Single bond, triple bond. 2 regions. So how many hybrids do we need? 2. Regions dictates number of hybrids. So we're only going to combine an S and how many P? We just want to combine an S and a P. This is sort of like what I did at the very beginning of my drawing. I just combined an S and a P. Okay? We're going to mix these, and instead we're going to have a scenario. If you combine an S and a P, how many hybrids are you going to get? I haven't said it this way yet, but if you combine two, you're going to get two. Always. If you combine 6 atomic orbitals, you're going to get 6 hybrid orbitals. You have to. It's math. We're going to get 2 hybrids. Let's draw them. Somewhere in between SP, what percent S character? More S character. These are looking more and more like S. These are actually getting shorter and fatter because they're starting to look more like S. We've got p orbitals left over. 2 of them, though. The electrons are going to sit like this. The valence electrons of carbon. Two hybrids. Hybrids set your geometry. How do you spread 2 things out the best?
Linear.
Linear. 2 balloons would spread out linear. That is, we're going to have one this way and one this way. Those are your 2 hybrids. That's called an SP and that's called an SP. 2 SP hybrids. This one's interacting with the electron from H to make a 2-electron covalent bond. We can do like that. What is this one interacting with?
Carbon.
Apparently the other carbon, which is the same exact setup. SP, that's an SP. What do we got here? Sigma bond. And what orbitals are interacting? Well, I just wrote it. SP, SP. Or this is an SP and an S, right? What else is left on this carbon? 2 p orbitals. The first one is in the plane of the board. And this is the same exact over here. That's a P, and that's a P. And guess what? These are interacting. Make pi bond. By the way, the sigma bond was here. So the hybrids have made sigma bond to H and sigma bond to carbon. Now we got a p orbital to the other carbon. I mean a pi bond to the other carbon. Pi bond. What else is on the carbon that we haven't drawn yet? The second p orbital. Well, guess what? If that's all on the plane of the board, the second one is orthogonal, perpendicular. It's coming out at you. That's a little bit tougher to draw. I'm going to draw it sort of like this, and in the book it'll be better. It's supposed to be coming out at you. It's going to not look good, or I'd have to redo it a couple of times, etc. But guess what? These 2 that are coming right out at you are also interacting. And again, I'm just going to have to do something like this, here to here. All right? So we have 2 pi bonds using the 2 p orbitals. So how many bonds do we have between the 2 carbons? 1 sigma, 2 pi, for a total of 3 triple bonds. So whenever you look at this, how many pi bonds do you see? 2. That's why a triple bond is 2 DUS. Because really every pi bond is a DUS. That's what's really a DUS. All linear. Linear meaning what type of bonding? 180. Okay. Go fast through this because ultimately you got to be reading. I mean, again, I could spend a week on this and we don't have time to spend a week on this. You can read and ask questions, fill in the gaps. Okay, this is my version in a quick manner. We'll do some summation next time, particularly looking at in the table. I got some drawings in there, including 3 different hybrids, and you can see the relative shapes, how they start getting fatter, more S character. The table's important, understanding bond lengths. Percent S character, very important right there. Percent S character tells you your answer. And then start doing hybridization questions, like at the bottom and in the workbook and in your textbook. See some of you in lab tomorrow upstairs. We'll get going at 2:30. Last questions today. We got 30 seconds, so let me see if there's anything else. Just again, please start working questions. You've got DQ, there's a hybridization question right there. Organizing your thoughts. So next time you can say, hey, did I organize my thoughts right? See you soon, guys. Have a good day.